Today we're going to briefly learn about naming organic compounds. Technically, you don't need to know it for year 11. It's a huge topic in year 12. It's called module 7 in year 12 is called organic chemistry, and a huge part of that's naming. Um, but in year 11, you're asked to, you consistently see these organic compounds and you're asked to kind of assess them for other things. So when we learn about something called intermolecular forces, you basically look at the type of bonds in organic compounds and you start to infer physical properties like boiling point, melting point, density, and other things like that. And so it's really useful to just have a basic understanding of it. And what we're doing here is naming probably doing about 40% of the naming, like enough info that you would be able to pick it up. First thing that you need to know, or actually, I'll go into a bit of background. A bit of background is that for organic compounds, um, by definition, they contain carbon hydrogen bonds. And because carbon can make four bonds, it becomes the best element to make large compounds. And you'll see it in everywhere. It's all in and living things, and in because of that, medicine. And it's got its own naming system, so it deals with the complexity of compounds. First thing to understand is that you use prefixes for how long the carbon chain is. So if it's just one carbon, you would use the prefix meth. If it's two carbons, you use the prefix eth, prop, but. And then after, just like in covalent compounds, after four is all just shapes. So pent, hex, hept, oct. Great. So you've identified the longest carbon chain. You then, if you're given the structure or the formula, you try to identify how those carbons are bonded to each other. So if they're just singly bonded, you use a suffix ane. So you might have methane, ethane, propane, and they're all drawn with just the carbons in between them are just drawn as single bonds. And the inference is if you get no other information, then you just draw hydrogens and make sure every carbon has four bonds off it. By the way, from methane to octane and even beyond to nonane, decane, and however long you want to go, all of those types of compounds are just called alkanes. Okay, so let's try that. Alkanes. And alk just means any carbon chain length. For the next one, by the way, its general formula is CnH2n plus 2. So for propane, there is 3 carbons, so the number of hydrogens should be double that plus 2, 8. Next one is double bond. If there's a double bond present, you use ene. This enables me to add a bit more to the naming complexity. For ethene, there's no other position than either in the middle of them. That actually goes the same for propene. So if I drew that double bond here, it'd be identical compounds. Might be worth pausing for a second to get that in your head. If you flip it 180 degrees, this is exactly the same written. Just be mindful that you're used to reading left to right. But if you could go around and look at that on the other side and read it right to left, you could still make the argument that this is it's the same compound, no matter which way you look at it. For the next one, but, 4 carbons long. The double bond is in this. I purposely drew it over here to call this carbon 1. Most people might think that's either carbon 3 or carbon 4 on first thing because they're used to reading left to right. But when we get rid of left to right thinking, this becomes carbon number 1. And off carbon number 1 is a double bond. If it was off carbon number 2, it would be but-2-ene. And note, if it was over here, that goes back to carbon 1. Okay, so this can either be carbon 1, this can either be but-1 or but-2-ene, no other options. And then I drew a bit more extra because a lot of people go, well, what if you have double or, say 2 double bonds? For this one, there's I use the prefixes di, and tri, and that to represent the dis and tris and tetras. They're actually you find them in covalent compounds. Okay, so covalent compounds uses dis, mono, di, tri, tetra, that kind of stuff. You typically only see di and tri. So that position and that position are the only positions they can be. So there's prop 3 carbons long, and there's 2 double bonds. For the next one, 4 carbon long. On carbon number 1 and 3, there's 2 double bonds. Triple bonds use the suffix "-ine". General formula is 2n minus 2. And yeah, not too much about them. So you identify longest carbon and a bit more about how those carbons are bonded to each other. And then the assumption from there is that they're all hydrogens unless you specify that there's a functional group coming off. And in year 12, you probably explore about 10 functional groups. But for now, we're just going to explore the 2 most common ones, and that's the alcohol functional group and the carboxylic acid functional group. For alcohol, this notation means that off somewhere on the carbon chain is this OH group. We give it the suffix "-ol", and an example of that is ethanol, so 2 carbons long, singly bonded ethane, and then we change the suffix "-ol" to represent that there's an alcohol group. Note that all 6 of these positions in this example are equivalent, and it wouldn't matter where I drew the OH. So to be more clear on that, if I drew the OH on this side, I just make this carbon 1, or it's like flipping the compound 180, or me looking at it from the other way. And 1, 2, and 3, the 3 spots around each carbon, there's no preferred spot. So there's rotational freedom, 360 degrees for them to move around. And so there's nothing, it means nothing if I drew the OH up there or that. I just trying to keep it in a linear fashion rather than make it look more awkward than what it is. For carboxylic acid, you got this functional group of C double bond OOH. This hydrogen is the acidic hydrogen. If you're wondering why this hydrogen is acidic and not all these other hydrogens, so acidic hydrogens mean that they're really reactive and not held on tightly. It's got to do with this polarity in this bond, and it also has to do with this C double bond O. So basically there's all these negative oxygens drawing away all these, pulling away electrons towards each other. So this oxygen would be have a lot of electrons around it. This oxygen would have a lot of electrons around it. And because there's 2 oxygens that are hogging, this hydrogen actually starts to be very positive in nature because it has no electrons around it. And because it has no electrons around it, it's able to be lost. We call it reactive. This one is fairly close, but this oxygen doesn't pull it away enough. You kind of need 2 oxygens to pull it away. So an example, carboxylic acid, propanoic acid, 1, 2, 3, prop, single bonds, AN, oic acid because there's this carboxylic acid functional group. And note, I do not need to specify where it is because it has to be on an end or a terminal carbon. And in this example, it doesn't matter if I drew it on this side. Either way, it becomes carbon number 1. And there's many more functional groups, as I alluded to, and there's this whole complex naming system. There's this huge booklet you can buy for $30 or even download a PDF of, and it goes on for days and days about all the rules if you have this compound and then, all that. So anyway, we're just going to name the most common ones, the basic naming system. Actually gets you a long way. So for this one, it says, give the names for these 3 compounds. I'm going to go quite fast. So 4 carbons, but, all singly bonded, ane. I don't put the E there yet because I see this alcohol group, and I realize this alcohol group could be on any number of those carbons. And I'm going to say it's on carbon number 1. Note in this example, you could only have, if the alcohol was there, it would be butane 2-ol. If the alcohol was there, it'd be butane 2-ol again. If the alcohol was there, it'd be butane 1-ol. In this next example is ethane, so 2 carbons, all singly bonded, and I use the suffix oic acid to represent this carboxylic acid functional group. Note that it also has a common name of acetic acid, and that's just because there was common names For some compounds, there was a lot of literature before the naming system was established, and so they agreed to just keep the names. And this happens for about, honestly, in my world, probably about 5 compounds that I deal with have common names. And you're not expected to always know them, but for a few of them, like for instance, water is actually an example of that. So water is right and not dihydrogen monoxide. That's inorganic. Okay. That's an example of a common name. And all I want you to do, even at the year 12 level, is just recognize these names as synonyms. So acetic acid is a synonym for ethanoic acid. And both, if you wrote either or, you both would be correct, even at the year 12 level, the HSC level. In this example, 5 carbons, pent. I don't know how they're bonded to each other until I assess the chemical formula. I see that their chemical formula is H2N, and I write ene. I can't specify whether it's pent 1-ene or pent 2-ene. I don't have enough information, so I'm just going to have to settle for that. In my next one, I've got hexane. Just draw 6 carbons. They're all singly bonded. That's actually 5 carbons, 6. And then because I have no more information, I just put 4 bonds in every carbon and write hydrogen for all of them. Boom, boom. Just to bang on about general formula. So for alkanes, general formula is CnH2n plus 2. So this should be C6H14, and it is. The next one, pent, 5 carbons. On the second carbon, which could either be that one or that one, there's a triple bond, and purposely chose the one on the right just to break the habit of you reading left to right. Me as well. And then everything else has 4 bonds. Every carbon, I go to check that every carbon has 4 bonds. Note that the 2 around the triple bond are fully already have 4 bonds, fully saturated. I shouldn't say fully saturated. I should say cannot have any more hydrogens. Ooh, some ugly hydrogens. General formula is H2n minus 2. So this should be, 2n minus 2. So this should be C5H8. And then I just put this in. This is acetate or ethanoate. This is exactly like ethanoic acid minus hydrogen. So technically it's the salt of. How you draw it is the kind of structure, how it's drawn, it kind of gives it away, right? So you start seeing things, instead of being like this, you start drawing it kind of like this condensed skeleton notation, which kind of gives you more information about the structure. So that starts to become more common as you move into year 12. All right. I've been lazy the whole way. Technically, you should go through and draw in the lone pairs of electrons, but the HSC is not too fussed with it, so I shouldn't be too fussed with it. But for completeness, and I generally also like to put a circle around the charge, which is also common practice. So ethanoate, you also need to know that's acetate, I guess, and that's one of your polyatomic ions, by the way. Yeah, might just finish it.